Okay, thank you very much, and so thank you the chairman, and of course I would like to thank also the organizer, which to give me the opportunity to present this talk. So I work in Dresden, and however, and I'm going to speak about an example of parity time symmetry breaking, such as the dynamic vortex-Mott transition, but I will use this as an example to show that architectures, even with the same element, if carefully designed, can lead to interesting broken states. So, and then so the question will be, what can we expect theoretically of time broken states from, for example, a twisted cuprate heterostructures, which is what I'm working right now. And also I will explain why these heterostructures are so difficult to make, and specifically the problem of the oxygen. I will show our measurement of the Josephson coupling between the twisted cuprate heterostructure. I will show that we have detected second harmonic modulation at very high temperature and specific angle, and also discuss some work in progress about the detection of the topological state. And also I will finally discuss the possibility to integrate this heterostructure in hybrid superconducting and thermal circuit with the exotic mechanical electronic properties of this actual heterostructure. Okay. Yeah. So first of all, I would like to thank my group that made these works possible so far, and the collaborators which range from a very different of institutes, from Dresden, Cornelius Nitsch, Valerio Vinocourt from Terra Quantum, from the University of Napoli, Domenico Montemuro, Francesco Tafuri, Valentina Brosco from Rome, Uri Voli from the Max Planck, Genda Guk from the Wehave National Laboratory, Kenji Watanabe and Takashi Taniguchi from NIMS, Philip Kim from Harvard University, and Pavel Volkov from Rutgers University. And special thanks also for some technicians that helped me a lot during this work. So first of all, an example of an architecture where you could see a dynamic broken states of the parity time symmetry is an array of superconducting islands on top of gold. So you can realize thousands and thousands of superconducting islands. You have proximity effects in a square array lattice structures. And what happens is when you apply a magnetic field that you create a Josephson vortex. You create a Josephson vortex, which of course has some sort of directionality, so chirality, and this Josephson vortex will fill all the gap in this square array. So depending on the magnetic field, you may fill as many Josephson vortices for each plaquette in your system. For example, in the case of filling factor 1, so basically means one Josephson vortex for plaquette, you can then apply a current through your superconducting electrodes in the array, and then you can switch a vortex Mott insulating state, so basically a frozen square array, very precise square array of Josephson vortices, to a dynamic response of the Josephson array in a vortex metal. Then if you do the scaling analysis, you discover that this kind of transition, which is a dynamic transition because you are applying a magnetic field and driving the vortex lattice with a current without any kind of thermal creep, because you are below the threshold of where a thermal creep can happen of the vortex lattice, then you see that the exponents belongs to the Mott class, or liquid glass transition class, universality class. And then the dynamic Mott transition has been identified as a PT symmetry breaking phase transition, given to the non-equilibrium nature of the system. And this experiment has been reproduced very recently, and using a different array structure. And in triangular structure, you do see exactly the same thing. Okay, now, so you can, by just playing with the architecture, you can realize time-broken states. So I didn't change, I just used niobium. So I didn't use, I just niobium. But I organized niobium in a special way, and I saw some spontaneous time parity broken state. Now, There has been a lot of work, very long, but the trick was that I get rid of the detrimental disorder by some fabrication technique. So the disorder, how you control disorder, is very important. And this is very important also for twisted architecture of cuprate structures. And there has been many, many theoretical proposals that have discussed the inhibition of node-to-node quasi-particle tunneling at finite twist angle, because you have these nodal gap structures, and in this nodal gap structure, you can basically play a little bit to suppress the quasi-particle tunneling, given that you select some specific angle. Now, the fact that you have a D-wave superconductor is known in these cuprate structures by a variety of techniques: spectroscopy, scanning tunneling, thermodynamics, and so on and so forth. And more recently, some theoretical proposals suggested that at some specific angle in this vertical heterostructure, so along the z-axis, in this vertical heterostructure, topological protected superconducting state at very high temperature may arise. And a spontaneous and dynamic time reversal broken states at matching angle can be detected. So spontaneously or dynamically. So for example, at some angle, you may expect a dynamic broken state. At some other angle, a spontaneous broken state. So this means, practically from an experimental point of view, if you just stack two flakes on top of each other, and you give an angle, and you don't do anything else, you may get a spontaneous broken state. Instead, if you stack just two flakes at some other angle, and you apply a current, you may deplete enough particles from the nodes such that you open a gap, and then you have a topological state. So in that case, it's a dynamical broken of the symmetry. So you put a die-wave superconductor on top of another die-wave superconductor, you get a special order parameter with an imaginary component. You can realize a phase diagram, and then you discover that this, in the current phase relationship, the current phase relation become different in a range of angle that is different than the other. So for example, in this case, close to 45-degree angle with some sort of uncertainty, okay, by the theory, for several reasons. That if you want to make questions, I will reply. Now, what this experiment has been done on the vertical axis, because this experiment has been going for a long time, and people have realized also in-plane Josephson junction using grain boundary junctions. In that case, the C, so the coherence length in plane, is around 2 nanometers for the cuprates. So you are forgiven if your sample has some imperfection, like as much as when you realize aluminum oxide junctions. But in the case of the vertical junction, you have 0.1 nanometer coherence length, so basically 1 angstrom. So if you get an imperfection on your crystal of 1 angstrom, so one atom moves just a tiny bit, then you have destroyed the coherence of the superconducting state across the layer. In fact, people have been not measuring the wave superconductivity across the layers in the z-axis, and they realized the main experiment where if they measure the JC as a function of the angle, the JC is more or less constant, except only in the case of the Whisker cross junction, where do see some dependence as a function of the angle, but that was not a true D-wave dependence, had some sort of large, let's say, discrepancy. In fact, if you, also more recently in Shanghai, an experiment on thin flake show, again, no angular dependence. So one of the things that is in common about all these experiments is that after they stack the bulk crystal or the thin flake on top of each other, they anneal the flake at very high temperature in order to restore superconductivity and the oxygen at the interface. And this means that they had to restore the superconductivity by reintroducing the oxygen. So they apply very, very, very high temperature. But people generally, I come from a material science X-ray radiation community, so I know how much oxygens are sensitive, how much oxygen interstitials and oxygen defects have a real and k-space order. Generally, people call them oxygen ion conductor, and has been works in the past showing that the disposition of the oxygen order in this material is really important and beneficial for the superconducting characteristics. In fact, oxygen is a very light element and is one of the most vagabond of the elements. So it's very difficult to keep it in place. So when you grow your crystal, generally the crystal grows and put the things naturally where they should be. But as soon as you start to touch these crystals, then you don't know anymore what you're doing, basically, because of the oxygen extreme sensitivity. Oxygen, in fact, in some cuprates have formed real and K-space orders which are strongly correlated with the high temperature superconducting property of the system and form stripe structures across the rock salt layer that you can detect with X-rays as peak and map on top of your sample. It turns out that if you want to change this K-space order, you can irradiate your crystal structure with X-rays, but you can start then to move the oxygen and cluster them together in kind of ordered structure only if you are around the temperature where the oxygen are mobile, which is between 200 Kelvin and 300 Kelvin. And this is shown here. So we apply X-ray fluence, we have an intensity, there is a threshold time, and at some point these oxygen puddles start to basically increase. This is an X-ray peak, which is increasing as a function of time. And then if you quench immediately your crystal temperature, you get superconductivity that is depending as a function of the K-space order of your oxygen. So this means that if the temperature is very important, and what you do at which temperature is very important when you process this material. And so the BISCO structure, when you try to thin down, it becomes insulating. This has been shown by Novoselov in 2005 when stamping it with a Scotch tape on top of a substrate. He was able to isolate thin flake of BISCO, but they were pretty insulating. Recently, with my work and the work of a group in Shanghai, we were able to isolate high temperature superconducting thin flake and measure the high temperature superconductivity in a kind of reproducible way. You can realize structures, devices, and so on and so forth. However, then it turns out that it's very incredible because generally high temperature superconductor, when you decrease the thickness, also they decrease the superconducting critical temperature. It's very difficult to have 1 nanometer or 2, 3 nanometer high temperature superconductor which have the same bulk TC. But for the BISCO, it's possible. In fact, if you look at by X-rays with 100 nanometer X-ray beam at the Buchanan National Lab, we scan and we map the crystal structure of the system. It basically shows, sorry, this is a little bit, it shows basically that the variation of the K-space order on the thin flake respect to the bulk states, it's only of 0.001. And so it's in reciprocal lattice unit. So it's just a Gaussian. So this means that this incommensurate lattice modulation that is typical of the BISCO structure remains basically almost intact when you thin down the crystal down to this level, okay? And now, how do we, this is a material that is clearly sensitive to air, so to water molecules, but is also sensitive to all the possible polymers or solvent that you're going to use in order to realize any possible fabrication, which is the typical standard method that people in the clean room use to realize nano devices. So you have to really go beyond any state-of-the-art known fabrication technique to deal with this material. So I developed a new technique that is based on this sensitivity of the oxygens by taking in consideration the following thing. The oxygen RK configuration must be frozen below 200 Kelvin during the BISCO interface formation. And the lattice of the BISCO crystallinity must be preserved against any reaction with water molecules. In fact, you have, even at very low vacuum, you keep having water molecule eating the surface. And this water molecule will react with an oxide, no matter what you do. They will diffuse and they will detach. Now, the technique, this is a kind of also a lucky discovery, because at the beginning I was not sure about that, but it turns out that the PDMS, EPDMS is a polymer, okay? It's a kind of, it's not a regular polymer, it's a siliconate polymer in some sense. And the PDMS become basically like a scotch tape when it's close to this glass transition temperature. Generally, when people stack graphene, TMDCs, all these other 2D materials, they use polyacton polymer like PC or PPC, and these polymers have a glass transition in which they melt. So when by melting, they basically surround your crystal, and by refrozing them again, then you can pick up your crystal. But this transition, when they melt, appears around 200 Celsius, at very, very high temperature, which is completely intolerable for the BISCO, at least from my point of view, okay? And then, however, the PDMS has the special property that this kind of glass transition occurs at minus 123 Celsius. So counterintuitively, the PDMS becomes basically more liquidish, okay, the more you go low in temperature, okay? Of course, it's still a solid. It's just a very tiny kind of soft behavior. And so it turns out that you can have a BISCO, you can use the PDMS, you lower in an inert atmosphere the temperature to minus 100 Celsius about, you can tear apart two flakes. In less than 1 minute, you restack them on top of each other using some robot that we have built. You choose the angle, and if you do all this, then you release your flake at minus 30 Celsius, the PDMS become less sticky, and then you have a perfect transfer technique. Then you use shadow mask evaporation with some evaporator integrated with your inert environment, and you can realize electrical contact. Now, if you are rich, you can have an ultra-high vacuum system. I have a high vacuum system. So I had to figure out, in a high vacuum system, you still have water molecules, even if you have 10 minus 7, okay? So, and the water molecule can already make a difference. So for example, this tells you how challenging it is to realize cuprates devices. So the superconducting TC is 90 Kelvin. Perfect. So if you say, okay, I see this, I publish. Great, I made an heterostructure, 90 Kelvin. But the point is that these systems, which is not encapsulated, is very different from this system in terms of Josephson characteristic. You will see the Josephson junction in both systems, but the Josephson characteristic here is 1.2 kilooampere per centimeter square in intrinsic, the intrinsic bulk junction. But if you use the other characteristic, the other sample with no encapsulation, because you didn't have an ultra-high vacuum system, okay, then the water molecule will degrade your system, and you will have a much decreased critical current density. We just published this now for the moment in arXiv, but whatever. So, an example. So, for example, we made many samples. So you have a cryogenic transfer, pure encapsulation, pure evaporation at high vacuum. You get all the same kind of superconducting critical temperature. You do see the dynamic resistance, the very strong coherence peak, and the hysterectic behavior. The same happens if you have a cryogenic transfers, pure evaporation in ultra-high vacuum. You see many, 24 samples here. We made some statistics. We have a sigma of 2.9 Kelvin in terms of TC, and a strong hysteretic behavior as well. Okay, this is just to make a panoramic, but this is just to give you a glance of what I'm going to say in the next slide. So you see the critical current of this sample. As soon as then you see that it's the same scale, it starts to become lower. And this is a function of the angle, okay? And so you have to imagine this as flake that are twisted to some extent, or twisted with some encapsulating boron-nitride structure on top. And then it turns out that you start to see some D-wave angular dependence already from the raw data, okay? Which you see better here. You see here the D-wave angular dependence that goes basically, that change the critical current of about 2 orders of magnitude, more than 2 orders of magnitude, down to 45 degrees, where you have the node suppression, and rise again. And the same happens for the other method with the encapsulation, where we do see basically the critical current decreasing, as you may expect in a D-wave vertical junction. Also, the temperature for a 45-degree junction tells a lot. Of course, temp cannot tell all. For example, I cannot see light oxygen elements. So when you see a temperature, right, it's very nice, but where are the oxygen, right? So you can see this, but my sample can be insulating, okay? So this is the problem of this material. So, but anyway, this is nice and unprecedented, the quality. So you can see the D-wave, the super lattice incommensurate structure modulation that is appearing exactly at the interface where I have exfoliated and restacked the sample. So these are the bismuth, the strontium, the copper, and the calcium atom, oxygen. Now, another aspect that is interesting of this twisted nodal structure is that you have a nodal superconductivity. And this is very special because people remember that high-temperature superconductors are high-temperature superconductors. So thermal effects start to play a very important role in the nodal structure. So what you see here is the ICRN is not simply going like in the Ambegogar theory, like decreasing as a function of temperature, but is having some non-monotonic effect. This non-monotonic effect depends strongly on the angle, so it's peaking around the, let's say, intermediate angle and returning back to the normal, let's say, decrease of Ambegogar around 45. And this is given by the fact, I can explain you later, but it's basically given by the depletion by thermal fluctuation of Cooper pairs by small gap and big gap, depending on which side you are, if you are in the node, in the antinode, or if you are in the node. So basically, you are depleting, and this depends also on the phase. So because this is, you have seen here phase, nodes, and antinodes. So you have to make some subtraction plus, and this is explained by theory, can be explained by theory. And also you see the non-monotonic dependent in the Shapiro steps, which we measured 70 gigas in the junction. So this kind of behavior is also seen in the Shapiro steps. And the Fraunhofer pattern at a low angle, let's say a 42-degree angle, a 41-degree angle, see a normal, a normal shape, as you expect, of an intrinsic Johnson junction. And the the Shapiro step at 70 gigas show integer filling, like you expect in a reasonable Johnson junction. So what you could say here is that you have first harmonic modulation of the current phase relationship. So it's a Johnson junction, okay? Now, if you instead get the angle close to 45 degrees, what happens, this is especially a 44.9, what happens is that you start to see many more oscillations in the Fraunhofer pattern, some asymmetry in the Fraunhofer pattern, which I don't know if you can appreciate, but this has some deep meaning, okay? And then fractional or half period Shapiro steps that you can see in this kind of fume that you see in the 2D color plot, okay? So now, if you have, how much time do I have?
Use 5 minutes for discussion.
Okay, so I finished. So I just want to say that we are doing some work in order to characterize this possible topological state. This is not a proof of topological state, but it is a strong indication, given that I did whatever I could to remove the possibility that there is some disorder at the interface. Because second harmonic can easily arise because of disorder, but I have, if you want to ask me more, I can show you why we believe that is not. And we have other evidence that I don't show here that show definitely that is not, and that we have a topological state at this temperature. But for the moment, this is enough. And so for the future, what we want to realize is complex circuit. So now for the moment, I just make 4 contacts on top of each flake, and that's very simple. But what we want to do is a complex circuit that can be fabricated at the interface of twisted heterostructure. This requires a completely new technology that we are now developing. We're using membrane, so we realize thousands of circuits. We stamp them at cryogenic temperature. We bond them. And then we can realize even solution of 150 nanometer to realize possibly superconducting resonator and so forth. And we have shown that we can stack this membrane. We have this via contact that perfectly touch at minus 90 Kelvin the flake, so we don't use any polymer, no solvent, no temperature, nothing, okay? And we can measure 91 Kelvin exactly like you expect in a bulk thin flake. And you can see the whole anomaly, and this I'm not going to discuss very much, the whole anomaly by the sign reversal change, which is a typical feature of the cuprate structure. So this opens the possibility to go in hybrid superconducting circuit that Davide was speaking about before, and also for this very sensitive heterostructure. So Okay, so this is just some schematics of what we have in mind, but so basically with this I would like to thank you very much for your attention.
Let us thank the speaker. And his talk is open to discussion.
Could you possibly have a way of detecting an S-wave component in the order parameter?
Allora, so if you see, it's a matter of, okay, this is it's a question that I thought a lot about. And so this is not zero, okay? So there is a finite resistance here. Theoretically, what you would expect in a D-wave superconductor is that it goes to zero, right? Now you have two interpretations for this, that you have a S-wave little component arising in this part, or you have co-pair tunnel tunneling. Okay? So these are two Cooper pairs that tunneling at the same time. Now, so on data that I don't show, I believe the second option that is the case, but the question is fair, and from what you have seen, you cannot rule out, but from what I will show in the future, you can rule out.
Okay. I can just cite that there is an old experiment by Müller and Keller who claimed that there was an S-wave component in 3D materials, but not in 2D. So if you put a second flake, you should look at what is happening, maybe.
I agree. I understand. This has been a very long standing discussion. To my opinion, I'm more interested also in this discussion. For me, it's interesting, but not so interesting. And I explain you why. Because at the end, what I really want to do is hybrid superconducting circuit. And for me, I need a way to have the highest DC with the lowest critical current, trying to avoid as much as possible disorder, so that I have the purest Johnson junction I can imagine. So I don't want to too much discuss about this, but definitely what my data show is that from no angular dependence at all, there is now a strong of spanning two angular dependence that you could at least say D-wave-like. Okay.
Okay, are there further questions? Please, you were please.
Thank you. So thank you for the talk. It was fantastic. Is there a specific signature of the topological superconducting state on the Fraunhofer physics?
Well, I think so. I think so. But this is because I mean I don't want to say something wrong. Okay. But in my opinion, oh man, so it worked so far. We managed.
Don't worry.
Okay. So, I mean, if you have a good eye, okay, you could see that this lobe, right, on this side are losing the steps on the other side. So there are a little bit of asymmetry from the two sides, from the IC plus and IC minus, like you showed in your, I know.
This was my question.
I know, but since this from here is not so evident, I didn't want to make a big deal out of it. But I have other data that shows that is much more evident. Right?
Thank you very much.
Okay. I think we have no time, and I invite my co-chair, Joris van der Bonden, to give a certificate.
It's the certificate. Thank you very much. Thank you very much. Thank you very much.